Well, this week on Physics Frontiers, we're going to be talking about the de Broglie-Bohm pilot wave theory. Most people aren't even aware that quantum mechanics has sort of an alternative theory or an alternative interpretation. I think of this as an entirely different theory, but it's been looked at as a different interpretation because experimentally it makes the same predictions as the Copenhagen interpretation of quantum mechanics, which is all of the stuff that drives people crazy about quantum physics. Um, the Copenhagen interpretation looks to me like a collection of equations which are very functional at replicating and predicting experimental results because it was basically designed upon experimental results. And it's sort of hobbled together conceptually to make that math make sense. And so you get stuck with ideas like superposition, and you get cats that are simultaneously alive and dead until you look inside the box. You get stuck with paradoxes. And I think that that's largely because there wasn't really an effort made to make a comprehensible theory. There was almost a tyranny, I think, of the mathematical approach to physics at that time, led by Bohr and Heisenberg and Pauli, to come up with a purely elegant mathematical description of microscopic nature. And there was sort of a disregard for the idea of it being readily comprehensible, as if only pedestrian mouth breathers would need to have a model that they could visualize and intuitively comprehend. There was kind of this conceit for physical credibility. And so we ended up with ideas in quantum physics which don't appear anywhere else in our experience. And that was kind of its boasting point, was is we're so advanced now that you can't even make heads or tails out of what we've got. There's a wave particle duality, and so even particles themselves don't have a classical interpretation that you can get your mind around. Now, de Broglie, early on in 1927, was a brilliant physicist, and he came up with a way of describing the effects that they're observing in quantum physics using a combination of a particle and a wave that he called a pilot wave theory. And it was surprisingly well received at the time, but very quickly I guess the establishment, the academics, decided they didn't like it and just kind of turned their back on it until 1952. The pilot wave theory gives you a model where the particle has a wave-like, almost like a wave-like field that surrounds it, which guides its motion through space between one point and the next. And whereas in the Copenhagen interpretation, the electron doesn't exist in any specific point or in any specific trajectory between point A, where it's emitted, and point B, where it's detected. In the pilot wave theory, the electron has a definitive position and momentum and trajectory from point A to point B the whole time, whether you're looking at it or not. You don't need to make any measurements, but its movement is guided by this wave function. And the wave function creates kind of a counterintuitive trajectory from point A to point B. So I guess in a nutshell, that's the idea, is that particles in de Broglie's thinking, which was later elucidated by David Bohm in 1952 and onward, there's a particle that's constantly interacting with a field of its own creation, its wave function, which is coupled to the entire universe. So it's a non-local theory because all of the other wave functions of the universe have an effect upon the wave function of the particle and its trajectory, but it is deterministic and a lot more sensible. And we're going to talk about the oil drop experiments, which I think brilliantly illustrate the idea.
You're saying you want to talk about the oil drop experiments that are really classical experiments, people dropping little drops of oil onto a vibrating table with oil on it.
That's right, because I think that if Yves Couder and Emmanuel Fort, the researchers in Paris who had come up with this kind of experiment, if they had had this demonstration available in 1927 to show the leading minds in physics, I think that we would have seen a completely different trajectory for quantum physics. I think they would be teaching pilot wave theory in schools, and I think that people would find it a lot more intuitive.
Like I said in my email, I'd like to do a completely separate podcast on the oil drop because I think they're interesting in their own right, and I think it's an interesting thing to try to get to.
I would like to at least put a link down below so that people can see the oil drop experiment footage. And you can really see that a system can have a particle aspect and a wave aspect, and you can actually just see that working in the little video clips of the oil drop experiments. And you can see how they're coupled. We're taught conventionally in quantum physics that you can only observe a wave aspect or a particle aspect depending on what your measurement is. But there's this idea that they can't both be true simultaneously. And what I love about the oil drop experiment is it shows you that no, this one system can have both aspects. It doesn't have to be mystical, you know.
That's the appeal that the de Broglie-Bohm interpretation has had, right, is that by separating out those two aspects, by having a pilot wave and the particle itself, which is supposedly bouncing around, now all of a sudden you have something that's a little more tractable. You can look at that and you can have some sort of intuition about what's going to happen in different situations based on your experience, rather than based on a complicated series of equations. Actually, they're not that complicated, the equations, but the implications of those equations aren't always readily apparent because they don't quite apply to things in the sort of normal way. This beyond that.
I think that there's a philosophical position where we can get started. I mean, it seems like in the late 20s and 30s when quantum mechanics was being developed, there was a rejection of the idea that we needed a comprehensible model to explain and visualize what was happening in the microcosm, and that whole idea that you needed something that you could, really that you could get your classical intuition around, that got thrown out. I think it kind of got looked down upon by the academics, and honestly, I think that Einstein and a lot of other physicists that I find myself relating to feel like that's a betrayal of the entire point of physics. I mean, there's more to physics than predicting the correct outcome of an experiment because, like Carver Mead said, if you're a good enough mathematician, you can mathematically describe almost any system. But does it have any relationship to what's really happening? Does it help you understand the process of nature to get that result? And that's what I love about the pilot wave theory, is that it's true to that primary mission, I think, of physics, which is to get a deeper understanding of the processes happening in nature, and where the math isn't completely divorced from the factors that you're manipulating in the lab, but rather tell you something about those factors and help you understand them. So that's why I think we need an interpretation of quantum mechanics, is that ultimately physics is a very special kind of conceptual art. And there's something to be said for having a model that can be grasped by the mind, that isn't just purely a mathematical object. And I think de Broglie was on the right track with giving us something that we could get our head around.
Are there any particular phenomena that gave this idea traction? You're saying we have this trifecta. We have this group of three people, which would be Bohr, Heisenberg, and Pauli, who are pretty much giants in the field at that point. But I mean, I don't think that's quite enough if you don't have any reason why people would be attracted to that idea when they wouldn't do the same thing in, say, electromagnetism or in thermodynamics. People wouldn't be attracted to that. In fact, people really hated that idea in those two cases, right? And it made it very, very difficult for science to progress because people hated that idea. Are there any particular experiments, particular effects possibly, that were so counterintuitive or so strange, people were willing to look at this interpretation of quantum mechanics, which is basically we have a set of equations, and so whenever we do an experiment, we prepare it as close as we can to the same state. If we're going to have an electron, we try to get the electron in as close to the same state as we can by doing exactly the same things every time. Then we wander over to the output of the experiment, and we just measure it, and then we sort of see if the histogram of results matches probabilities based on this equation and this rule for calculating possibilities.
Right. You're talking about the double slit experiment, right?
That's every equation, basically. But one way to look at the double slit experiment is you say, okay, I've prepared my electrons with this electron gun, and I'm just going to leave it at the same voltage. It's going to have the same temperature. It's going to eject the same number of electrons. It's going to eject them at the same rate, and they're going to have the same kinetic energy, and they're going to go through this double slit, right, where I've got partitions blocking the electrons. And then they're going to go hit some sort of screen or some sort of photographic plate or whatever it is that it's going to be when they first did the experiment. Then I observe these light and dark bands, which make them look like a wave phenomenon, and then I'm going to just calculate where I think these bands are going to be and how bright they are based on these equations. And I'm not going to worry about whether or not this electron went through this slit or that slit. I'm just going to say a possibility of going through either one of those slits or possibly both at the same time or whatever it is, because I don't really want to think too much about this. All I really care about, the only thing I give any ontological validity to, is this wave function. I don't give the electron any ontological validity. The only thing I care about is I have this wave function, which is a square root of a probability, basically. It's a complex field, which means that it's a complex number that has a different value at different points, right? So every point in space has a complex number associated with it. And when I square that, every point in space has a probability of where that electron's going to be.
Well, yeah, you're talking about the Copenhagen interpretation, which is popularized because basically with the double slit experiment, when scientists put photons through a double slit, and they discovered that even when you put one photon at a time through a grating with two slits in it, and it still produced an interference pattern, that pretty much blew everybody's mind, and everything was up for grabs at that point. So the whole idea of the physicality of reality and all of it was secondary to the crisis of how do we explain this. If you've got something which is a particle and you're sending it through one at a time, how do you get an interference pattern on the other side? Because there's no clear and intuitive way to do that. If you've got one object like a bullet that's going through two holes in a screen, you should just see two regions of intensity right on the other side of those two slits on the background where they get detected, but instead you get this range. So all of these ideas came out, and the Copenhagen interpretation was maybe that photon is going through both slits simultaneously and interfering with itself before the wave function collapses when it hits the screen on the other side and we detect it. That's not a necessity of the situation. That's just one potential explanation. And the pilot wave theory gives you a way of looking at it where, well, maybe the particle itself goes through one slit or the other, but the wave function associated with the particle can go through both at the same time and interfere with itself and basically create troughs of probability or troughs of low energy where the particle is more likely to go. And that's intriguing. The idea there's ripples. You end up with a model. I was watching a brief interview with I think his name is Basil Healy. He was a physicist who worked with David Bohm, I believe, on this theory for quite a while. And I think they worked on the book The Undivided Universe together. And he was saying that the new model we have is that particle and wave particle isn't really the right way of looking at it, but rather every particle is a process. There's something going on there. And although it has certain properties which are constant in time, it's cycling, and it's like a standing wave. And so you could have, just like a photon transforms itself constantly from an electrical charge to a magnetic field to an opposite electrical charge to an oppositely oriented magnetic field, you could have a particle that's doing the same thing. It exists as a point, and then it oscillates into a field condition, and that field condition interacts with its environment, and so you get the pilot wave, and that shapes its trajectory.
One thing I'm interested in finding out about this is what sort of ontological status does the de Broglie-Bohm interpretation give to both this particle and this wave? When you look at your oil drop thing, your particle is just this drop of oil that's bouncing on top of some vibrating oil. And so the wave is the vibrating oil, as I understand it, and the oil drop is the particle. So the question is there any deeper meaning as far as de Broglie and Bohm and possibly Healy or whoever it is that's carrying on this sort of tradition right now? Is there any idea about what those two things are? I assume that the particle, when you talk about the particle, is the electron.
Sure. Well, that's true of, I think, any body of matter. De Broglie introduced us to the idea that really any fundamental particle has a wavelength associated with it. And although the wave-particle duality is only easily experimentally evident in small, very lightweight particles like photons and electrons, that there's a wave function associated with all matter, right? I think that the ontological significance that's tricky, because I don't know, can we detect the wave aspect of a particle at a distance? And that seems like that was the main problem, is that maybe you can only detect the wave function that's the pilot wave if the system is coupled to that particle. Because isn't the pilot wave an aspect of the particle that moves along with it?
That I'm not really sure about. And you also end up with all that nonlinearity stuff that you were talking about earlier, right? I was wondering if the pilot wave was decoupled or not. So, the way I would understand it, thinking about it, would be to look at the pilot wave as not just being a pilot wave, but being something out there interacting with something. I mean, I don't really know what. I'd expect, doing something with the electromagnetic field or something like that with the photon field, where the electron would be bouncing around on that. But you're saying that what we're looking at is really we can only detect the bouncing around a bit, the little particle, the electron, and you cannot detect the pilot wave. So do we really know anything about that pilot wave? I mean, that's really what I want to know, is what would that pilot wave be? Not necessarily whether or not we can detect it, because obviously we can't, because if we could detect a separate pilot wave, or even disprove there was a separate pilot wave, we wouldn't have to worry about it, right? Because now all of a sudden it wouldn't be an interpretation, it would be a theory, right? But the question is there any relevance to, or is there any... What I mean by ontological relevance is there anything about this pilot wave that the theory postulates that tells us what it is being different than its interaction with the particle? Interaction being different with than its interaction with the electron, or with the photon, or with the quark, or whatever it was. I mean, this came about long before quarks, but still, is there something that would give it some sort of meaning that we could actually grasp onto?
Yeah, well, in recent years, you've seen the weak measurement experiments. I believe that Aronov came up with to do a sort of a statistical experiment where you could move your detection screen on the other side of a double slit experiment to various distances, and you could reconstruct the path that the particles must have taken in order to get to the screen in that configuration. And it fits, and it matched perfectly with the predictions of pilot wave theory that showed the trajectory of the particle through the slits as it was influenced by the interference pattern of the wave function of the particle. So you get there's these beautiful trajectories that come out both of the slits that aren't straight lines. They have a ripple to them, and that's kind of weird to think of it that way. But apparently, if you use a weak measurement technique, you can sort of infer that the path of photons or electrons through those slits takes this really interesting kind of meandering ripple trajectory from the slit down to the screen.
So by doing the weak measurements, you're saying we can take a peek at what these trajectories actually look like.
That's right, which kind of illustrates, those trajectories kind of illustrate the interference pattern of the quantum potential, which is an expression of the wave function. So you can sort of see how it works. You can get a sense of that field by looking at the trajectories.
Okay, that makes it sound a little more like the field is something that the electrons or whatever are bouncing around off of than something that's sort of falling around with the electron. It sounds like something the field ends up being something they're interacting with. I'd really have to think about that. So what we're seeing here then is that there's something that these electrons are interacting with, and they have these trajectories that are based on that thing that they're interacting with. So a particle's interacting with another thing, it looks like, and that especially and that's what this interpretation says. And then they go off and they do things. However, this interpretation doesn't really make any different predictions than standard quantum mechanics. So this is an interpretation of non-relativistic quantum mechanics, and it makes no significantly different predictions that we could actually look at than regular quantum mechanics, based on the Schrodinger equation, and just sort of eliminating any ontological status to the particles between the preparation of the experiment and the measurement afterward. One question that I was really interested about, and I'm not sure if you know the answer to this, is what would the explanation for quantum tunneling be in the de Broglie-Bohm theory? Do you know that?
Well, I think that there's a relationship between the particle and its pilot wave, which, if we look at the oil drop experiment, it could show that there is almost a cycling level of energy depending on its position. So maybe I know that there's an experiment where they called them walkers, these little oil droplets bouncing across a surface, and the surface is energized when the timing is just right. When the particle bounces, I guess at just the right moment when the pilot wave can give it a little more energy than usual, it'll have a probability function for getting enough height to jump over a barrier. And I guess just quantum tunneling is just a matter of energy. So if the particle has enough energy to move through a barrier, then it'll do so. And I guess there's a time function associated with the wave equation that, if the particle arrives at the barrier at the right moment when there's a high energy contribution from the wave function, that it can tunnel right through. But it's hard to visualize that, because in reality an electron isn't a bouncing particle on a surface, riding on its own plane wave, right? It's doing something else in a three-dimensional sense, and we need sort of a better analogy to really understand what's happening, the real relationship between the wave aspect and the particle aspect.
I think partially the reason why I was asking that was because in that oil drop experiment, it was hard for me to try to get an idea of what tunneling would be other than randomly bouncing over a wall, which is what a potential barrier would look like. And obviously you can't send that backwards into quantum mechanics, right? Because in quantum mechanics, you have that wave function, or in the Copenhagen interpretation at least, you have that wave function. And that wave function tells you that if you have a potential barrier, then something that hits that potential barrier, even if it would be classically disallowed, that if that potential is too high and the speed of the electron is too low to jump over that or to pass over the barrier, it doesn't have that much energy. There still is that probability that the electron or the particle of whatever particle you want will end up on the other side. And so I was wondering whether or not there would be something really, really interesting in that. such as the particle being absorbed temporarily and showing up on the other side, or if it was just the sort of bouncing over the wall sort of thing.
I think what we're seeing is that the energy of the particle is, although the energy on a time averaged basis may be insufficient to penetrate a barrier that requires a certain amount of energy to get through, that that at any given instant there's a possibility that there will be a higher energy level than the time averaged energy level. And I guess that happens, if that peak in energy happens at just under the right circumstances, where the trajectory is correct and everything, then a particle can move through, right? I mean, if you've got an electron and it needs to penetrate a body of matter, it's going to be facing basically an upward hill of potential energy created by the electron charge field of all the matter that it needs to get through. But there are pathways, right, where there's lower energy, and if the electron has enough velocity and momentum at just the right moment, and at the mouth of one of those trajectories, it can get through it, right? Isn't it just a matter of having enough energy to get by?
Yeah, it just has to sort of get over. But the idea of quantum tunneling is this electron does not have the kinetic energy, the speed to get over a potential barrier. Classically, has a probability of passing through it. So all I see here is just one more argument that there's some extra ontological status that we have to give to that pilot wave, that it's not really just a part of that electron. It has to be something else that has that kinetic energy, or at least has the ability to have some sort of temporary account balancing, like taking on a negative kinetic energy, which would be sort of crazy, but not crazier than anything else. When you're dealing with some of these things.
Well, we know that there is a vacuum fluctuation field, right? There's a quantum fluctuation field of virtual particles. Isn't that the analog for the energized oil in that experiment? Is it that there's a background field of energy, and that a particle can borrow temporarily energy from that field and get excited if it gives it back, right, within a certain time?
So the bouncing oil drop doesn't have to give that energy back if it ends up someplace weird, right? It doesn't necessarily go back into that field. Now, I'm not sure with this pilot wave whether it's possible to not give that back, right? But it would probably give that back in the tunneling. That's not the thing that I'm thinking about. The thing I'm thinking about is if the particle can pull energy out of that pilot wave, then it seems to me that the pilot wave and the particle have to in some way be separate entities. They can't be the same entity, right? Because the pilot wave would have to move along with the particle, and it would have a similarly limited amount of energy. And then you also have to think about, well, how does the pilot wave get to the other side of the potential barrier? Just seems to me to look like this pilot wave has to have this separate ontological status and in some way be one of these all-encompassing weird things like an electric field or something like that.
Well, it seems like it might be some kind of interaction, right? I mean, maybe the pilot wave is the product of the interaction between the field of the particle and the field of all of the other particles that it's coupled to basically in the entire universe, but certainly at its nearest areas. Maybe it's an interdependency. Maybe if you had one electron alone in an empty universe, maybe then you couldn't have a pilot wave because it wouldn't have any other fields to interact with.
And again, that would go on to this whole idea that there's something there. Now, I mean, you can keep adding more things, right? So you say there's this field that's independent, and then maybe there's this pilot wave that is sort of in that field, and then that's what's actually interacting with the electron. But that doesn't get you away from having this sort of field from everything else. So you still end up with this sort of all-encompassing thing all out there. It's not too much of an issue as long as you're wandering around talking about electric fields and temperature gradients and things like that. You can still talk about something like that. But at some point you really do have to sort of figure out what it is. And right now, I know that I don't have a really good idea about what that thing is. And it sounds like probably nobody has a really good idea what it is. It's something that, as far as I recall, people say you just can't in principle measure it, which is always a little bit scary.
Yeah, but I think they would have said the same thing about the vector potential until Aharonov-Bohm came up with that effect where they can detect it without a magnetic or an electrical field. The Aharonov-Bohm effect that we talked about in quantum paradoxes, right? So maybe there's some way that we haven't figured out yet to interact with the pilot wave, with the quantum potential, that will prove that it has a physical existence, right?
There could be, but I mean, you just have to figure out what that would be, right? Okay, well, I think we've done a reasonably good introduction, at least, to that. Okay.
All right, James.
Yeah. All right. Well, thank you very much.
All right, James. Thanks for your time.
Okay, Randy. Thanks.